This is Mr. Pillar for ECET273 Modern Energy, lecture number 10, the induction motor. Based on chapter 7 of the Square DeWitt text or chapter 14 of the Fardo-Patrick text. In this lecture, we're going to describe basic construction features of the squirrel cage induction machine, explain principles of operation of the polyphase induction machine, calculate synchronous speed, explain the concept of slip, calculate the operating speed of a motor given the slip of the frequency of the rotor currents, and look at nameplate data. Okay, so induction motors have different types for different purposes. This is mechanically what it looks like. The case that the motor is in is what we're going to describe here. We have basically totally enclosed and open frame. Totally enclosed allows no deliberate exchange of air between the inside and the outside of the motor. Open frame allows air to pass through the motor. Totally enclosed would TEFC, totally enclosed with fan cooled, TENV, totally enclosed non-ventilated, TEAO, totally enclosed with air over. Basically that one would be used on a fan. So if you primary purpose of the motor is to drive a fan to blow air through a room, why don't you use that fan to also keep the motor cool? Open frame types would be an open frame drip proof, which would allow water to run off from the top and not drip in. Guarded and splash proof, they generally have encapsulated windings, and explosion proof. Here is an open drip proof frame to look at. Totally enclosed, fan cooled. Notice here on the back of this motor has a case that covers over fan blades. That's finger safe area. The fan blades will blow across those radiator fins on the totally enclosed to keep the keep the motor cool. Here's a totally enclosed, non-ventilated. All right, so here's an explosion drawing of the induction motor. This would be the total enclosed fan cooled. So the very back on the left there is the finger safe guard for the fan. There's a fan paddle wheel to blow air across the fins of the motor on the stator. The stator is the central point that has the mounting. That in an induction motor is the armature, right? There's current induced onto the stator. The rotor itself is there in the center. Notice there are no slip rings. There are no wires that are going to connect that rotor. It has induced current that through transformer action of the current that we apply to the stator, the armature will induce current to the rotor and cause the field to be formed to allow this motor to spin. Here's a cutaway of a fully assembled then. You can see the totally enclosed the rotor. Again, no way of getting electricity to that rotor. Now let's look at a nameplate. Here we have some wiring diagrams on the left. That would be two different ways of wiring up this particular machine. If you note, the voltage of this machine is 230/460. So you either put the coils in parallel or the coils in series, depending on the voltage required. This is a 50 horsepower machine with 1,765 RPM. There's a frame type. We'll talk about that later. Up in the top right hand corner it says totally enclosed, fan cooled. So this could be very well the motor that we saw in the explosion drawing there. Time rating, it's a continuous operation, 3-phase, 60 hertz, and the ampacity is rated at 122 amps or 61 amps. The 122 would be at 230 volts, 61 amps at 460 volts. Note on the bottom there it says it can be used for a 208 system, and we'll talk about that as we go a little further here. What can we do with the nameplate data? Well, the first thing we can do with the nameplate data is find the power factor of this motor at operated loads, and then we can repeat it for the 208. Note this is all at rated conditions. So your nominal efficiency, Pn, is equal to 50 horsepower times 746 watts per horsepower. That's a standard horsepower to watts conversion, divided by, this is a 92.4% efficient machine. And we know that because at the very bottom of the nameplate there are three efficiencies. We have the nominal efficiency, the minimum efficiency, and the guaranteed efficiency by the company. 92.4 is its nominal efficiency. So we take 50 horsepower divided by the 746 divided by its efficiency of nominal efficiency, and we get a kilowatts of 40.37 kilowatts. For rated voltage and current, calculate S, and it's three-phase. So S three-phase is radical 3 times 460 times 61 amps. Remember, that's the ampacity at 460 volts, and you get a value of 48.6 kVA. Therefore, the ratio of P over S gives you a value of 0.831 lagging, and it's lagging because this is the motor, which is mostly induction. For the 208 version, go ahead and calculate the whole thing again, same pattern, but instead of the 460, use the 208 with the ampacity rated for 208, and you get your VA. And we're going to run at a power factor of 0.8. So if you pay attention here, you approximately have 1 kVA per horsepower at rated conditions. In our case, it's a 50 horsepower motor, and rated conditions 460 times 61 amps times radical 3 ends up with 48.6 kVA. So this motor basically holds true to that rule of thumb. Okay, there's your nameplate again. The NEMA code letter. Let's go back to that nameplate. This NEMA code letter is a code letter G, and it is a NEMA design B. Alright, so code letter G on this table, this is a standard NEMA table, code letter G has a kVA per horsepower locked rotor current of 5.6 to 6.29 kVA per horsepower at locked rotor current. What does that mean? Well, let's step up here and look. What is the starting current for this motor with letter G? Assume worst case operations. Worst case operations on that, 6.29 kVA per horsepower times 50 horsepower equals 314.5 kVA. 314.5 kVA divided by radical 3 times our voltage rating, and we shifted the decimal to make things a little better there, ends up with 395 amps locked rotor. Now what's locked rotor mean? Well, locked rotor is essentially your starting current. We all know that when you start a motor, it has an inrush current, we call that. Well, the technical term for that inrush current is locked rotor current when we're speaking about motors. Inrush current is what we talk about for inductors itself. Motors, we refer to it as locked rotor. Essentially what it means is if you had the capability of grabbing a hold of the shaft of the motor with a wrench and holding it at 51 horsepower negative its rotation and keeping it from moving, you would draw 395 amps. This motor draws 61 amps at rated condition. So if you divide that out, the locked rotor current is exactly 6.47 times the rated current. Induction motors will, as a rule of thumb, draw 6 to 8 times rated current to start. Now here, here's your principles of operation. Now, I made reference to the fact that the rotor itself has no direct electrical connection to the world outside of the motor to allow us to induce current onto that rotor. So how does current get onto the rotor? Well, it goes through a transformer action. Okay, a transformer, consider a primary and secondary. The primary has a magnetic field that rises and falls, and that rising and falling magnetic field cuts the lines of conductor on the secondary, which then induces a current, and so then the secondary has current. Let's roll that up into a motor format. The stator has a rotating field. The field is rising and falling at different locations along the stator, around the circumference of the stator. That is causing a magnetic field to rise and fall in the conductors of the rotor. All those squirrel cage devices of the rotor, the bars across the rotor that run horizontal and then are shorted together on the back end of the rotor, cause a current to flow, much like is secondary of a transformer. That current then has a magnetic field itself, and the NS on this drawing is the speed of the rotating current of the stator. The rotor itself will have a different speed called the NR. So let's look at this. If we locked the rotor still, that's what this drawing is showing, the stator flux rotates at synchronous speed. That's the NS is equal to 120 times the frequency divided by poles. The stator flux induces current in rotor windings, creating the magnetic field. The conductor's velocity through flux, because the flux is actually moving and the conductors are not. Okay? What does that do for us? Well, magnetic force pulls the rotor around at less than synchronous speed. We call that NR. NR must be less than synchronous speed, otherwise the conductors don't cut the flux. So imagine at that start, the rotor's not moving, the stator has a rotating current, a rotating magnetic flux. That rotating magnetic flux is cutting the conductors on the rotor. The rotor itself creates a current, which then induces its own magnetic field. So the south pole of that magnetic field is attracted to the north pole of the rotating magnetic field on the stator, and it follows behind it. You have to have the north pole cut the lines of conductors to induce a current that will then create a magnetic field that will be pulled along with it. That is slip. The rotor is slightly slower than the rotating field on the stator. So slip is equal to the percent ratio of your NS minus NR divided by NS. Okay? Your synchronous speed minus your rotor speed divided by your synchronous speed. For most induction motors, it's typically 5%. At blocked rotor, you'll have a frequency on your rotor of 60 hertz. Locked, the rotor current down there in green is the frequency of the rotor current is slightly less, the same slip difference in the speed of the RPM. Alright, now I've talked about that, let's do a real quick example so that we can get a better idea what we're talking about. This is a 60 hertz induction motor. It operates at rated speed of 1765 RPM. At what rate do the stator and the rotor fields rotate? What is the frequency of the rotor currents, and how many poles does this machine have? Well, we start with the easiest answer. Our stator field is going to be your synchronous speed. Your synchronous speed is 120 times the 60 hertz divided by poles. Well, if two poles, if we put a 2 in there, we end up at 3600 RPM. Well, 3600 RPM and rotation of 1765 RPM gives us a slip of 50%. which is much higher than the 5%. So this is just inductive guessing. If we divide by 4 for the number of poles, we end up with 1800 RPM. 1800 RPM minus 1765 RPM, the rotor speed, the rated speed of the machine, divided by 1800 RPM, and you end up with 1.94% slip. This now makes sense. So we now have two answers here, right? The stator speed is 1800 RPM, and the slip is 1.94. So the stator and rotor fields are rotating. The stator is rotating 1800 RPM with respect to the stator. The little guy at the top is standing outside looking at the stator. The rotor rotates 1765, so with respect to the rotor, the fields appear to rotate at 35 RPM if I'm standing on the rotor. That gives you kind of an idea of the difference between the two speeds in reference of where you are in location. The frequency of the rotor is slip times frequency. Slip is 1.94% times 60 hertz. Our rotor has a frequency of 1.164 hertz. That is the induction motor. Please go ahead and listen to it again and take your notes and come to class prepared to discuss this on Monday. Thank you.